banned technology, the light bulb that lasted forever. Chapter 1. The Eternal Glow. You hold a glowing orb in your hands, warm as a distant hearth. Tiny currents dance along its glass skin, carrying stored energy like a whispered secret. You feel the gentle pulse of electrons racing through a slender thread of tungsten, each collision creating steady light instead of fading warmth. In this quiet moment, the bulb is more than metal and glass. It is a promise of endless day. Across history, inventive minds have sought the unending flame. In the late 19th century, Joseph Swan and Thomas Edison each coaxed light from their own filaments, wrapping precious carbon and then tungsten into thin spirals. Their workshops glowed with experiments, each spark a step toward illumination. You imagine those early laboratories, the hush of cautious triumph when electricity met matter without complaint. Your breath settles into the rhythm of discovery as you consider filament physics. Heat energizes atoms, freeing electrons to leap between energy levels and release photons. Each photon escapes at characteristic wavelengths, painting the world in warm hues. Yet heat also drains the material. Tungsten atoms wander, weakening the spiral until the filament surrenders to gravity and darkness. Beyond incandescence, modern LEDs promise greater longevity. Semiconductors guide electrons across junctions, yielding light with minimal waste. Here, quantum mechanics whispers through crystal lattices, channeling energy into precise colors. These diodes endure for tens of thousands of hours, but even they face eventual aging as defects accumulate and carriers scatter. True perpetual light remains elusive because every light source obeys the laws of thermodynamics, surrendering energy in subtle forms. Entropy pulls at the edges of invention, reminding you that nothing truly lasts forever. Still, your mind drifts to theoretical designs. Solar arrays feeding energy back into the grid, nuclear isotopes glowing within safety shields, or vacuum tubes cooled to near absolute zero. In this reflection, you recognize a delicate balance between human ambition and natural law. As you rest in that silence, a question lingers, guiding your curiosity toward what lies beyond. Chapter 2. Welsbach's Whisper. You stand before a workshop table where Welsbach's gas mantles rest like faint ghosts. Each fragile mesh teases your eye with potential light. In 1885, Carl Auer von Welsbach isolates neodymium and praseodymium from cerium earth. Rare earth elements numbered 60 and 59. You imagine the first spark of flame through that mesh, transforming cotton and oxides into brilliant glow. You hold in mind the gentle law of blackbody radiation, where any heated solid glows across colors based on temperature. A Welsbach mantle coated in thorium oxide reaches over 2000 kelvins and radiates bright white light without flame color. This thermal emission, a pure fact of physics, fills early gas lamps with steady glow. You feel the steady pulse of atoms vibrating, each electron dancing in thermal embrace. You breathe in the fine dust of rare earth nitrates resting on a shelf. These lanthanide salts, once thought obscure, reveal the subtle chemistry of 15 elements hidden in small crystals. Welsbach's work depends on precise separation techniques, fractional crystallization, and selective precipitation. You envisage a lab bench strewn with flasks, solutions shifting color as acidity changes. Each drop is a gesture toward purity, a step closer to capturing fleeting light in your palm. You sense the transformation as those cotton bags impregnated with nitrates enter a hot flame. Inside, dehydration and thermal decomposition turn them into thin oxide filaments. This chemical metamorphosis, governed by reaction kinetics, forges a scaffold that glows under combustion. Welsbach watches atoms rearrange, testing glow intensity and heat tolerance. You imagine the invisible forces, activation energy and diffusion, collaborating in silent choreography to birth radiant webs of light. In that hush of creation, you perceive a faint resonance between chemistry and light. Welsbach's whisper echoes in each spark, reminding you that every material holds secrets waiting in its atomic lattice. The glow fades into your memory, stirring curiosity about what new alloys or phosphors might follow in his wake. You close your eyes, still feeling that delicate dance of discovery. Chapter 3: The Tungsten Tapestry. You step into a hall where threads of metal shimmer in soft lamplight. Each filament is tungsten, atomic number 74, chosen for its highest melting point among pure metals. You feel the weight of centuries of design resting in your palm. In this quiet expanse, you notice how temperature and resistance dance together. As heat climbs, resistance rises, guiding the filament's glow. You follow a slender strand until it becomes a river of electrons. In tungsten, free electrons drift through a lattice of atoms in a body-centered cubic structure, colliding and releasing energy as gentle warmth. This resistive heating turns electrical current into visible light. You taste the promise of knowledge in every photon born, each carrying a whisper of the physical laws that shape our world. Beneath your fingertips, the tapestry reveals microscopic grains and boundaries. Real tungsten grows crystals in tiny blocks, each about a few micrometers wide. These grains influence strength and flexibility, defining how a filament bends or holds shape under constant heat. You sense the resilience encoded in crystal orientation and slip planes, natural paths that allow atoms to shift without breaking. Rising through the hall, you find yourself in near vacuum. Here, the filament glows without air to oxidize it, a crucial trick that prolongs its life. Bulbs may also use inert gases like argon or nitrogen to slow tungsten evaporation, but the real lesson lies in minimizing chemical reactions. You imagine hours uncounted as the fine wire endures currents measured in milliamps, singing a song of efficiency and endurance. A hidden knot appears within the weave, a point where density and heat, stress converge. You pause, feeling the pull of a deeper engineering truth. Tungsten slowly sublimates, atoms drifting away until the filament thins and breaks. This subtle unraveling holds the key to renewed designs and longer-lasting light, a mystery that awaits your discovery in the next chapter. Your curiosity tingles at the edges of this metallic web, inviting you deeper into the very heart of matter. Chapter 4: In the Heart of Vacuum. You step into a chamber evacuated of air, where your senses rise to meet the hush. The glass walls reflect soft light as you pause, feeling the weight of quiet. A vacuum here means fewer air molecules, pressure dropping to a fraction of an atmosphere. You imagine those molecules drifting away, thinning like morning mist, until only echoes remain. Your breath settles into a calm rhythm as you consider the fragile filament at the chamber's core. Surrounding this tiny wire, the near vacuum prevents oxidation and chases away convective heat. In this purified space, thermal energy radiates outward in graceful waves, extending the life of every glowing particle. You sense how reducing pressure slows collisions, letting each electron dance farther between atoms. A distant hiss finds you through the walls, the steady heartbeat of steam ejector pumps. They vent steam that condenses and carries away remaining gas, drawing purity from the air. You feel the gentle pulse of oil-sealed valves holding firm, creating a boundary between silence inside and bustle outside. Here, mechanical craft meets molecular truth in each tight metal joint. Your gaze falls on a slender pressure gauge, its needle flickering between marks in pascals and torr. You recognize the science in that motion. Lower pressure grants longer, mean-free paths, where particles wander vast emptiness before they collide. Each calibrated line whispers about endurance, about the precise balance between vacuum and structure that lets experiments unfold. You glance at a tiny mass spectrometer, its slender filament ionizing stray molecules to reveal composition, pressure variations in real time. Time stretches like a slow breath as you sense the seal between glass and steel. In this void, you discover both shelter and challenge. The absence of air becomes a canvas for possibility, a silent stage awaiting movement. You stand at the threshold of what must come next, heart aligned with measured calm. And somewhere in the vacuum's hush, you sense a secret valve waiting to be opened, inviting the next soft exhale of discovery. Chapter 5. Quartz's Quiet Song. You gaze at a piece of quartz resting softly in your palm, its edges glowing in warm afternoon light. Each photon passing through crystalline walls slows, bending toward the center. You feel a stillness, as though time itself pauses in glassy silence. This gentle refraction is real. Quartz's uniform silica lattice guides light with minimal scattering, a quiet miracle. Beneath its gleam lies pure silica, silicon and oxygen entwined in a tetrahedral network. Each silicon atom bonds to 4 oxygen atoms, forming a rigid framework that endures both pressure and heat. This chemical architecture gives quartz its hardness, ranking 7 on the Mohs scale, and a stable structure that resists weathering. You sense geometry in every facet. You remember how quartz defies thermal shock when other glasses crack. Its strong psi-O covalent bonds rearrange under sudden temperature changes, preventing fractures. This resilience lets quartz endure searing heat in industrial furnaces and volcanic flows. Even volcanic lightning dances near quartz crystals without shattering them. You feel comfort in this fortitude. Quartz envelopes encase filament in halogen bulbs. When tungsten atoms escape the coil, halogen gas invites them back in a loop. This halogen cycle extends bulb life and maintains brightness. Quartz glass stays transparent to ultraviolet rays, revealing unseen spectra. You savor the metaphor. Light reborn again and again within its glass sheath. Inside each quartz crystal, you discover piezoelectric magic. Press its surface and electric charges flow along crystalline axes. Release, and bonds reform with precision, oscillating at a constant frequency. Quartz watches and radios rely on this hidden rhythm to keep time and tune signals. You trace this cycle of pressure and release, a soft heartbeat in stone. You imagine silica melting above 1700 degrees Celsius, flowing in molten currents that forge pathways for halogen cycles. You taste that purity, envisioning glass forming in volcanoes and labs alike. As bonds break and reform, you sense an endless renewal, a gentle dance of creation. Yet beneath quartz's lullaby, a soft tremor hints at revelations just beyond its quiet sheen. Chapter 6. Halogen's Hidden Breath. You inhale a warm metallic scent that floats lightly around the glowing filament. In that moment, you become aware of halogen vapor swirling in delicate eddies, a breath shared between light and gas. You notice a quiet warmth at your chest, an echo of the lamp's steady glow, reminding you of how energy flows in gentle cycles. This scent marks the beginning of a chemical rebirth, with each rise in temperature and each new whirl of vapor. You stand watching, aware that every inhalation traces the path of atoms in silent motion. Inside the lamp, tungsten atoms vaporize from the hot filament surface, striking halogen molecules and forming tungsten halides that drift in the glass envelope. As they cool near the cooler walls, these compounds break apart, redepositing tungsten back onto the filament and releasing halogen gas anew. This regenerative loop extends the filament's life, illustrating a simple chemical equilibrium at work. You feel a steady rhythm in this cycle, much like tides moving in and out. Here you glimpse how a barely visible reaction can sculpt enduring light. You picture individual atoms dancing along heated arcs, each collision a tiny spark of transformation. You sense how temperature influences reaction rates as molecules move faster when warmed by the filament's glow. In these microscopic exchanges, you find a reflection of your own breath, aware, measured, renewing. The lamp's light becomes a living metaphor for how energy and matter exchange roles in constant flow. You rest in that thought, feeling science as a gentle companion. Within that shared breath of halogen and tungsten lies a silent question. What other secrets do the molecules around us hold? You sense curiosity stirring in your chest, a soft invitation to explore deeper realms of molecular alchemy. In the quiet glow, you realize that every bond broken and reformed whispers a new story. As these subtle chemistries unfold, you feel the weightlessness of discovery and the pull of questions, yet to gently guide your path toward uncharted molecular landscapes as hidden wonders ripple beneath the surface. Chapter 7. Grid of Ghosts. You step into a twilight realm woven from steel towers and copper veins. You notice a subtle hum that vibrates through your fingertips when you touch a transmission line. This is the song of alternating current, a flow of electrons reversing direction many times each second. In this moment, you sense how invisible particles carry energy across vast distances, knitting distant cities together with their silent dance. The pulsing waveform rises and falls in a steady rhythm that echoes the beating of your own heart. You recall that standard grids use 50 or 60 hertz, meaning 60 cycles per second in many regions. Each sine wave peaks and dips in a perfect curve, a mathematical promise of stability that keeps lights glowing and motors spinning around the world. Beyond the hum, you detect whisperings of inventions that never reached your hands. Some designs languished in dusty patent offices, suppressed by shifting priorities, or lost to corporate chess games. You imagine blueprints of silent generators, superconducting wires, and wireless power transfer, all waiting in limbo. Each abandoned concept is a fragment of promise that the grid remembers in its constant, unspoken resonance. As you walk alongside the corridor of pylons, your heartbeat finds a companion rhythm in the alternating flux. This phenomenon, known as resonance, happens when two frequencies align, amplifying their shared vibration. You sense how the grid and your pulse coalesce in a gentle amplification of energy, reminding you that the natural world and human technology often move in harmonious patterns. In the distance, a faint glow outlines a junction where wires converge. You feel drawn toward a phantom blueprint etched into your imagination. It hints at pioneering ideas like high-temperature superconductors, where resistance drops to zero and currents loop indefinitely. Such breakthroughs could transform the grid into an almost magical tapestry of lossless energy, if only these secrets could be coaxed from hidden archives. You pause at the threshold, recognizing that each gentle current carries more than energy. It carries unrealized dreams and questions quietly awaiting your next step forward. Chapter 8: Patent and Power. You sift through dusty patents, each page alighting with faded ink under a dim lamp. A patent is more than paper. It is a legal instrument that grants inventors exclusive rights for up to 20 years, a protective shell around nascent ideas. You feel the weight of those clauses, binding sparks of imagination behind fine print. This quiet fortress shapes the path of progress in laboratories around the world. Each national patent office, from the USPTO to the European Patent Office, examines claims with precision, weighing novelty against existing knowledge. Within these contracts, you sense a story of light itself, the journey of photons across glass and air. Scientific advances like fiber optics rely on controlled refractive indices in glass fibers, a principle discovered when researchers observed how light bends at interfaces. Corporations stake claims on these findings, filing claims that bracket the speed of illumination, like invisible toll booths on beams of sunlight. Your mind drifts to courtrooms, where evidence meets argument under the sharp gaze of judges. Here, the quantum nature of light becomes a battlefield. Is a photon a wave or a particle? Debates over duality echo as inventors and conglomerates negotiate royalties for lasers, diodes, and photodetectors. Each contested claim adds tension, dimming the brightness of shared knowledge. You wander into a quiet studio imagined between legal pages, where an inventor tests a new prism designed to split sunlight into vibrant spectra. You recognize the simple science. Dispersion depends on wavelength, longer waves bending less than shorter ones. At this intersection of art and physics, you see how ambition can both illuminate and obscure, how guarded ideas can stall collective discovery, and you wonder if openness could shift power's balance. Finally, you hold a sealed document, its cover unmarked, its contents a promise of rekindled possibility. Somewhere within, there lies an unclaimed truth about harnessing solar energy more efficiently, perhaps through perovskite cells or tandem junctions that capture a broader spectrum. You feel a gentle pull toward what follows, sensing that beyond these locked pages, light awaits liberation. Chapter 9: The Underground Workshop. You step down a narrow staircase, lantern in hand, into a cool, quiet workshop carved deep beneath the earth. Glass bulbs hang from iron beams, glowing with soft amber hues that pulse like a living heartbeat. The scent of solder and warmed metal drift through the air, and a gentle hum lingers in the low ceiling. Each lighted arc and steady spark reminds you of the small rebellions of science that once flourished in hidden corners. Around you, workbenches groan beneath coils of wire, stacks of circuit boards, and glass jackets waiting to cradle tiny filaments. You recognize the shape of an early vacuum tube, its glass envelope whispering how electrons travel through a void. The principle feels familiar. Charges drawn toward a positive plate, glowing when heat sets them free. This simple truth, discovered over a century ago, still makes you wonder at the miracle of controlled currents. A soldering iron lies ready, its tip cooled since last night's experiments. You feel a kinship with each inventor who dared to create beneath watchful eyes, their curiosity burning brighter than any forbidding decree. Every component here, from mica insulators to copper traces, is a testament to determined hands and thoughtful minds. You imagine electrons dancing across those shiny pathways with silent grace. Light filters through a small grate overhead, hinting at distant roots and sediment layers that shield you from a world that once outlawed these gentle explorations. You trace your finger along a blueprint pinned to the beam, a sketch of a resonance circuit where inductance and capacitance meet in harmonic balance. The idea of resonance, where energy oscillates in perfect harmony, feels like a soft echo of your own breathing rhythm. Beyond the workbenches stands a sealed archway draped in heavy tarpaulin. Behind it lies the hidden heart of this workshop, the master design that unites every filament and coil. You pause, sensing the careful equilibrium between secrecy and revelation, ready to lift the veil and witness how light springs from hidden order. Your heart hums softly, eager for the next spark revealed. Chapter 10: The Light That Remembered. You stand beneath a single lamp that recalls every secret you've explored. Its gentle glow spreads like a warm embrace against the hush of the night. The lamp's glass curves softly around a tungsten filament, suspended in a vacuum, inviting you to observe its quiet brilliance. You feel the hush of potential in the golden light, and notice how its steady luminance reveals textures you had forgotten. In this stillness, you become aware of the story woven into photons. Inside the filament, electrons drift through a lattice of metal atoms, colliding and releasing energy as heat. This process of resistive heating transforms electrical current into visible light through a phenomenon called incandescence. You imagine the path of each electron, guided by voltage, tracing arcs of possibility across filaments. The more current that flows, the brighter and warmer the filament becomes, glowing at 2600 degrees Celsius. Through this precise balance of energy and matter, the lamp remembers the hidden laws of physics. That memory grew from decades of toil in workshops and laboratories, where engineers tested different materials and shapes, from carbon strands in early experiments to today's pure tungsten wire. Hidden innovations built upon one another like stepping stones. You sense the weight of every hypothesis and late-night sketch, that finally emerged as a single enduring light. Each revision in metallurgy and vacuum pressure contributed to a filament that now burns cleaner, lasts longer, and holds the dreams of countless inventors. Now warmth washes over you as your heartbeat slows, syncing with a gentle pulse of photons. Your breath matches the slow rhythm of atoms vibrating along the filament's thin wire. In this alignment of inner and outer worlds, you realize that every flash of insight once hidden in darkened labs now resides here in this serene glow. The lamp hums quietly, bridging the gap between human curiosity and natural law. And as you watch that steady light, you feel a question rise. What will you illuminate next? Beneath that question, the promise of undiscovered knowledge flickers softly, waiting for your hand to reach toward it.